Good morning. Thank you very much for coming to my keynote, and thank you so much for inviting me to this wonderful conference. I'm enjoying it very much, and I very much enjoying meeting the community. Luckily, I'm not going to talk to you about my PhD because I did my PhD on collaboration in the knitwear industry. And of course, I didn't know it at the time and I didn't have the vocabulary to talk about. But that was the perfect sandbox to study transdisciplinary design because it's a process shared by three people, a knitwear designer, a knitwear technician, and somebody who then sews together the jumper. And it was absolutely brilliant for studying transdisciplinarity, people from different social groups. The knitwear designers were university educated, the technicians were not. They were women, the technicians were male, and you got to study all of these different interactions. But since it takes about a day to design a garment, I could study hundreds of different designs and dozens of different people, and it gave me an enormous insight into how things are designed. And ever since I've been fascinated in how different people come together to design something, how you get hundreds and thousands of people to work together for a common goal, and it actually at the end of the day flies, because in a lot of other human endeavors we work together and nothing all that much tangible comes out. But in engineering, the fascinating things, at the end of the day it works, there is a product, it makes a difference, and I have never stopped being interested in all of the nuances of this process. And that's what I'm going to talk about today, but I'm mainly going to talk about engineering and not knitwear, so you're safe there. As you all here are very aware, probably more than many other communities, the products have become very, very transdisciplinary over the last century, more or less. If we, just as an example, if we look back to an early car like this BMW from the 1930s, that was a mechanical engineering product. There was a mechanical engineering company and had mainly mechanical engineers working in it. And of course, times have changed, and now cars are driving around an awful lot of computing. You have got materials engineers in it. You've got systems engineers, electrical engineers, you name it, a car industry company hires them. So we're living in this very, very transdisciplinary engineering world, and very, very few complex products will now really only be designed by a single academic discipline. But the interesting thing is that this isn't necessarily reflected in the organizational structure of the organization where the products are being designed. And this is just from the website of BMW, that I looked at their board of management and their advisory board and just looked at the disciplines that these people came from. And lo and behold, the board of BMW is still full of mechanical engineers and business and administration people. It was then pointed out to me that this is actually quite good going, because in the UK it probably wouldn't have had a single engineer on the board, but never mind that. But even on the supervisory board, you still have got a lot of mechanical engineering dominance. The power of the discipline still lies often with the historic original discipline. And you see this in a lot of companies. For example, a company that produces some sort of production machine that once upon a time was purely mechanical would still be run predominantly by mechanical engineers, even though it now hires computer scientists and AI people. And that has a huge impact on the methods that the people are using and the way that they are working. And that's what I'm going to talk about today, is the importance of methods. And methods very much are the way to sort of formalize and structure product development processes. And they are more or less systematic and they are more or less formalized down, but they are one of the ways in which people can share experience with their future selves, with their teams across organizations, and of course also across disciplines. And as an academic community, we are very involved in that a lot of the people in the design society where I'm mainly working in think that their raison d'etre is to develop methods and then publish the methods before they're ready to publish. But that's another story. And the challenge with methods is that people often develop a method for a particular task, which is great and helps a lot. But the tasks never come in isolation. They are all dependent on other tasks. So you kind of need a system of methods that work together. Otherwise, the poor methods get stranded, and the people who want to use the methods don't know where they get the input from, and they don't know where the information needs to go. And that can cause quite a lot of problems. So I'm going to talk today a little bit about working in multidisciplinary teams. I think just again preaching to the converted and setting up my frame of reference. Then I'm going to talk a little bit about methods and about what the Design Society community thinks of what a method is. And then I'll try to relate this to engineering knowledge from the philosophy community, because there people are thinking about what actually is engineering knowledge, what are the categories of engineering knowledge, and I'll see whether that will help us to think a little bit about what we need to do to get transdisciplinary methods, because I think what we need to aim for is what I like to call a transdisciplinary ecosystem of methods, where methods can work together across disciplines and make it possible for everybody to work in a way that they want to work. And again, this is a talk that is, like many other talks, not only my contribution, but it's based on the collaboration with many people from very different fields. So I am working quite closely with people in industry who are managing teams with people with different expertise, and I'm currently working on a publication with a friend who is working for a German machine company who has been put in charge of all of the non-traditional engineers, and she has to try to make all of them happy and collaborating and not lose patience with each other and not quit and respect each other. So I'll talk about some of the experience that she has shared with me. But I've also worked with other academics on methods and how we define methods, how we want to position methods. And I've also worked with philosophers on engineering knowledge, and I'll try to bring all of this together here. So, as I've just said, is that engineering is increasingly multidisciplinary. We haven't got much of choice. And it's multidisciplinary in all ways, even in the design of things that are seemingly quite simple. For example, if you look at a parking sensor, we all have got parking sensors, very standardized thing these days. We've got many, many different disciplines who have to work together in a single team in order to make this happen. We've got everything from car styling to the mechanics, to the people who built the sensors, to the signal processing, to the user interfaces. All of that has to come together around one single function. But everybody has got slightly different requirements to do their tasks. They have got different dependencies. They often constrain each other and often don't communicate this. And sometimes they collaborate well and talk to each other, and sometimes they don't, because they just don't understand each other particularly well. But it has become the daily business of almost all engineering managers to try to get some form of multidisciplinary team together. And people come from many different backgrounds, and that means that they have a different vocabulary, they use different representations, and they do things in a different way. And immediately would think, well, maybe it's different because they have got a different language, but there are so many other reasons why it's different. For example, the different universities have a way of approaching things. They have a world according to me view, which is taught to all of the students, which is fine, which makes sense, and then they come into a company, and then all of a sudden people have got a different worldview. And you quite often see that companies like to hire out of a single university because that is the way you get a certain degree of consistency. And I did a case study with a company in Liechtenstein. And now Liechtenstein, I don't know whether you're aware of its existence even, it's a teeny tiny country that I think was so teeny and tiny that people forgot to absorb it when all of the big mergers of the small countries in Central Europe happened. And it's right between Austria, Switzerland, and Germany. So it recruited out of southern German universities, Swiss universities, and Austrian universities. And even the mechanical engineers had a very different way of talking about things, just became they came from different schools, even though they all had at least studied the same subject. And then, of course, you have got different specializations having a different vocabulary. So a mechanical engineer who works on lifts would talk about differently to a mechanical engineer working on cars. And then, of course, we talk about the disciplines here. So mechanical engineers are different to computer scientists. But then also we find that companies are developing their own language. And that can be very confusing. For example, in the design literature, we usually say you first do your design and then you develop your ideas further. So design and then develop. And then I went into a company which kept on saying things that development came and then design. And I got so confused until I finally said, well, what's going on here? What do you mean? And then it says they develop their concepts and they do their detailed design. So first development and then design. Thank you. I was then on the same page as them, but it was incredibly confusing and it really didn't help. And then, of course, we have got industry sectors having a very different vocabulary, a different way of looking at things. For example, the aerospace industry is incredibly mathematical, it's very formal, it's very conservative, and doesn't at all go with all our love for innovation and experimentation and agility that we get in other industry sectors. And another thing that causes different vocabularies are, of course, different regulatory frameworks, which is something that we are acutely aware of in the UK now, since we might have to develop our own one and make ourselves even more confused than we are already. And so there are layers of confusions or layers of a lack of formal understanding that people have. And it can be really quite fundamental that, for example, my industry friend was saying that people from different disciplines have a very different view about the fundamental purpose that the product have, that they are developing, or the fundamental purpose of the activities. And they describe things within slightly different ways, whether you transform a signal, for example, in the parking sensor, or whether you stop a car from driving into the wall, is a slightly different perspective on the same problem, and you talk about it in very different ways. And they think of the technical systems in different ways, which confuses things a bit because it gives you a very different boundary to the problem that you're interested, that you want to work about. It also gives you a different perspective of the breakdown of activities, that you very often get a notion of, oh, well, and then you're just going to give me a sensor, because eventually the sensor arrives as a finished sensor to put into the parking sensor. And for the sensor engineers, that's his life. I mean, you can't just sort of say, you give me one, and not understand what's happening underneath. But another big issue is also that people have got very different orders of decision making, and they work in very different timescales. Some disciplines slowly converge to decisions as you iterate, as you keep on testing, and other disciplines develop something and then the whole lot has to be tested and then a decision has to be taken. So again, there are very different perspectives, and people don't agree quite in the way you have to iterate and when you have to iterate. So in some cases, iteration is an integral part, it's entirely normal, that's how you do it. Other people would see of this almost as a failure. So people kind of question each other and are lacking a certain respect maybe for each other because they do things that are unthinkable from the perspective of somebody else. And of course, they have to learn to express what they really need and what they want from each other. And it's often hard to know what the information is that somebody else ought to give you, and in consequence, what information you need to pass across. And you find this in a lot of organizations. If a product is sufficiently simple and an organization is sufficiently small, then people know what the other ones need to know. They walk across the corridor and say, say, oh, by the way, I was going to talk to you about X. I'm just going to change this. Does this affect you? And in 2 minutes, they clear it up because they know what the other one knows. They know whom to ask. And then you get to bigger organizations. And all of a sudden, it is something where it gets passed on to the boss. It gets discussed on a higher level. It maybe feeds down or maybe it doesn't. And as the communication channels become longer and more formal and you can't sound people out, it becomes harder and harder to work across disciplines. And what you see over and over is that if you ask people, how do you communicate with your colleagues? They'll tell you, oh, I'm just going to go down the corridor and I'll ask my friend, which is often for people they worked with from the same disciplinary background. And then you say, well, how do you communicate with the computer scientists? And then if you have given it a sufficient pause that they've forgotten that they told you something else 10 minutes earlier, they'll say, well, I have to raise this with my boss, who will then pass it on to the systems integration department, who will then feed it on to the boss of the people in computing. And you think, okay, how long does that going to take you? And then maybe eventually they'll get an answer back 3 weeks later, when for a mechanical engineering colleague, they had just walked down the corridor, maybe had a coffee and sorted out the problem. So there's a lot of practical challenges around cross-disciplinary communication. But to put this in a bit more formal way, Larry Buccarelli wrote this very nice book, Designing Engineers. And he says that essentially engineers have their own object worlds. I think for that matter, every human being has their own object worlds. But essentially, object worlds is a concept that describes the concepts with which people are thinking. And that's an interesting concept because it puts together the formal knowledge that people have, what they learned at university, but also their experiences. And therefore, it's something deeply personal. It overlaps with people, but it's never quite the same. And you can have greater overlap within one organization than within one discipline. But it's that interesting interplay between experience and expertise. And curiously, the research community had a bit of a blind spot on the experience bit. There has been quite a lot of work on expertise over the years, like what Cindy was talking about yesterday, but very little on the effect that experiences, working on a particular project, on a particular company, the bad experiences, the good experiences actually have on people. And in all of that, engineers become familiar with the teams in which they work. They feel comfortable. And I mean, we find this as academics as well, and especially as transdisciplinary academics. We happily collaborate with some people from some disciplines. And as long as nobody rocks the boat, we are quite happy. And it's the same for the engineers. They eventually learn to collaborate with the people in their team. For example, the people in the car sensor team would eventually learn to rub along each other. They know what the electrical engineer wants from them. They know what the sensor engineer wants from them eventually. But then we have got new kids on the block turning up. And in the moment, we are having a very interesting transition because we've got so many of the big data, AI people, a new breed of computer scientists coming in, data scientists that aren't quite understood. They don't know what they want. They don't know what they need to explain. In the case of data scientists, they think they're magical creatures who can conjure up knowledge out of unstructured data, and they are going to tell them the answer to all of the questions that the engineers haven't been able to solve. And it isn't quite like that. So disappointment is unfortunately incoming on that front, but it is that kind of integration of people that becomes more and more challenging. And of course, these days, engineers also have to work a lot with non-engineers. And we have got user experts, we've got sociologists, we've got policy experts. Of course, they always had to work with business people, and all of of that has to be brought together. And in a big organization, you don't necessarily need all engineers to understand all of those things, but you have to have enough of an overlap that the whole lot is connected, and that you have at least some people who can translate, so that the scary social scientists can talk to the equally scary engineers and negotiate maybe what you needed to do in a social context with the final product. And basically, if this all works, we end up with transdisciplinary teams. If it doesn't work, then we have to have a careful managed process that maybe can resolve the problems. But one way in which this could be improved is by having shared methods and tools, which they don't necessarily have in the moment, but ought to have. So now let's step back a little bit and think about what a method is. And method is, it turns out to be a very ill-defined term, that it's essentially a specification of how the actions that people need to carry out and the in and output information that they need from this, and maybe a bit of an explanation about the tools that they ought to use, and also about the sequencing of the tasks. And different methods are described to different extents, from things that are incredibly binding to things that are really quite loose. And we have many, many categories of methods, and that's by no means an exhaustive categorization. But we have basically got some kinds of methods that we all use. I mean, like brainstorming, or behind us we have got the stars, where we arrange post-it notes around stars as a, what was it, mind writing was what the method was called. So you have got that kind of method that we use very, very broadly, where we basically just told the basic idea and then people more or less pick it up. But we also have got very, very holistic methodological frameworks that contain many sub-methods that people are following. For example, in the moment we have a huge fashion for agile, which comes with a whole lot of vocabulary. It comes with a whole lot of processes that people follow. Sometimes they understand the spirit behind it, not necessarily, but you still have got this whole holistic approaches. Or we had Six Sigma in the early 2000s, which was incredibly fashionable, or QFD, these kind of approaches. And then we have got, of course, an endless amount of design for X approaches. And it's wonderful if you have a design for X approach that allows you to optimize for a particular criteria, whether this is manufacturability or sustainability. The problem is you have to optimize at the same time for all of the other X's, and how you bring these things together is often not explained. So methods can be a bit problematic. But methods also have a multitude of elements that is important to consider, because we need to get them right if we want people to use our methods, and if we want to have methods that can help people. So methods often have a core idea, and what I've just explained about the mind writing with the star is very much the core idea of it. There is probably also representations, in that case the star diagrams or other ones that I'm not familiar with, and you would have a procedure that you would typically follow, and there might be a suggestion of tools. And in that diagram we deliberately drew tools as going outside, because you often use the same tool in multiple methods. And Brian and I were quite active in the DSM community, which is a tool that's very widely used in a whole range of different methods, and sometimes interpreted in very different ways, but at least the common software is there and the common representation is there. But when you're designing methods, and therefore when you're evaluating methods, it's a very holistic process where you really need to go through many different steps. And in that diagram we have mapped this onto a essentially research approach, which is describing a very iterative development of design research outputs, where you start off very typically with empirical research, you develop some theories, you develop some tools, and then you develop their introduction. And you can actually evaluate all of these parts separately, but you can also enter what we call a spiral at any point, because sometimes you already know what the problem is. You don't have to do empirical studies. You go into developing a tool, but then you realize, I don't quite understand it as well as I ought to. So you go back doing some empirical studies, or alternatively, you developing a theory. You think you're going to develop a tool, and you realize actually there is one already. I can just jump straight through to introduction into industry. And I think the elements of a method map onto those different steps. And if we want to develop methods, we have to go through a process of understanding its constituent elements and also making sure that we evaluate them as we go along, and not just think my method is a great method if the product that's designed with it in the end is a good product, because it's not as simple as all that, because we have got some challenges with introducing methods. Essentially, there is a big problem of multi-causality, because was it my method that led to the great success? Was it their engineering talent, or was it the many other methods they used, or processes, or management styles, or whatever you wanted to attribute it? And one of the challenges with methods is that it's hard for people to separate the method from the people who are using the method. In this company in Liechtenstein, I did the interviews with a young German engineer who had developed a method, and I was trying to help him to evaluate this method. And we absolutely couldn't get the people to comment on the methods. They kept saying, but Basti is a brilliant engineer. That's why he got it right. And we kept saying, yes, I know Basti is brilliant, but what do you think about the method he used? Was that a good method? Yeah, but he knows how to do it. And we got versions of that from various people, which really didn't help us at all at the time for evaluating this particular method. And I think it's multi-causal, but there's also a problem about the notions of causality that people are applying to a method, because a method doesn't guarantee outcome, so there's nothing deterministic. Just in the same way as if you do a brainstorm, you can't guarantee that you come up with a genius idea as opposed to a whole lot of rubbish. You can't guarantee it in many other methods, so it's not deterministic. It's a causal push. It makes things slightly more likely. And if you've got enough things that give you a little bit of a causal push, you might just get somewhere. But we also have got a big problem with methods coming from the Hawthorne effect. I don't know whether you're familiar with the Hawthorne effect. It's a very important concept, so I'll just go over it quickly. It was an American company in the 1930s which had a very inefficient process, and people came along and changed the process, and lo and behold, it got better. And then after a little while, they changed the process again, and it got better again. And they were very happy. And then they did a third round of iteration, and the process again improved. The only problem was they put it back to where the process was originally. And it turned out that the point was not that they had a better process. It was that somebody had paid attention to them, somebody had praised them, and somebody had told them what they individually ought to do. And that helped. And a lot of the time, method introduction suffers from a Hawthorne effect. Somebody is listening to me, somebody is paying attention, somebody tells me what I ought to do, somebody finally says, well done, you finished your task on time, and people are motivated and happy. So we're struggling a bit with the evaluation in that front. But the other problem we have with methods is that it's difficult to get people to invest time into actually sharing their experience. It's difficult enough to get people to share experience with their future selves. I mean, stopping and writing down lessons learned that you might use 3 weeks later or 3 months later is difficult enough, let alone for a team in which you won't be part of, or sharing it across an organization where maybe the organization gets the glory, but you don't get the glory for having written it all up. And then, of course, on the receiving end, we have a bit of a problem of a not invented here phenomenon. Why should I listen to that lot? I know what I'm doing, and so method sharing can be a bit of a problem. And I think the academic community isn't necessarily helping industry or themselves in all of this as well, because we haven't really got good ways of predicting how processes will behave under particular circumstances. We have got fragments of it, but we really can't assess very clearly the applicabilities of tools and methods to particular processes, because it depends on the nature of a product, it depends on the way the organization works, and depends on a lot of the elements of a configuration of a design. So it's very, very situated, and we can't really easily predict it. It's a bit like doctors who can say, yes, I know that pill works, but unless we know when the pill works, for whom, under what circumstances, with what dosage, it's not going to be a whole lot of good. So I think that's what we have to work on academically, collectively. But we also have a culture of really premature publishing, that we are pushed so much into publishing our core ideas that very few academics have got the stamina to see things through until they're well worked out, well validated, and have got the representations, the procedures, the scope described, so that we kind of leave these fragments of information for people to pick up, and that isn't helping industry much at all. But we also have got knowledge islands that often academia works with particular companies, develops methods in response to their particular situation, and then you need to do a little bit of a transfer from that context into another context. And that is something for which it's difficult to get funding, to have time, to get access, to have skill, and then it doesn't happen. So somehow or other, we're hoping that these knowledge islands all by themselves grow together, and it's not always happening. And what we also don't have is a lot of benchmarking, and because at least in engineering design, we don't have a culture of really comparing what we are proposing to somebody else, because ideally we would want to have benchmarking problems so that we could compare the outputs. And thinking that this is important, I was involved about 10 years ago in a special issue on benchmarking functional modeling. So we picked a product, proposed it to everybody who contributed to the special issue, wrote a paper about benchmarking, and hoped that people would then come along and benchmark against our functional model. And it turned out that this was a great way of getting citations for our benchmarking paper, but it didn't really lead to benchmarked functional modeling approaches. So there's still more education to be done here. So essentially what we are hoping to reach is what we like to call an ecosystem of methods, and I think the current state we described as a menagerie of methods. Now, if you look at this picture, this is a classical 18th century animal menagerie, where you show off your wonderful animals. They all live in their enclosures, and people came along and said, look, this is a giraffe, look, this is a lion. And the giraffe and the lion were all very unhappy and eventually died. And that's not what we want. What we want is a flourishing system where the methods can work together. And that is a paper that I wrote with quite a lot of colleagues from the Design Society as a position paper in design science, where we were proposing that what we want is an ecosystem of methods. So one of the things we started off with is thinking, well, what do we want what would a method paradise look like? So I am helpful as ever, loaded up this historic picture of ancient visions of paradise where the lions and the sheep happily live together. I mean, nobody ever tells you what they eat, but that's besides the point. But at least it did remind us that we need to think about the input and output of methods. And we also realized we needed a lot of shared concepts, shared terminology, maybe also shared governance, since that worked very well in the paradise struct scenario. And then the other sort of metaphor we thought about is a medieval craftsperson who had a whole lot of tools, and we wanted our methods to work very much like a master builder would have used his tools. In that case, where it was very clear which tool to use under what circumstances. They understood the sequence of actions they wanted to do, and they could concentrate on what they wanted to do because they knew how to use their tools, because nothing is more of a distraction than if you have to try to learn the tool at the same time you're trying to do a task. I mean, everybody who's ever tried to learn a programming language in order to carry out a bit of PhD research knows what I'm talking about. Methods can be a hindrance as programming languages or tools to fulfilling your goal rather than helping. But what we want is a user who is empowered to concentrate on the activity and not on the tool. So essentially what we are hoping for is some sort of harmonious ecosystem in which the methods live together and can work together. And also where the users are able to adapt the methods to their particular needs, because we'll never be in a position where just a method can just be used as it is. It always has to be slightly adapted to a situation, but also where the methods are connected, where we don't have these method islands, just as everybody in an ecosystem has to have something to eat and realistically is eaten by somebody. So our methods also need to have this input and output clearly sorted. And for that ecosystem, what we need is a common terminology and a clear understanding of the input and outputs and a complete coverage of the method so you don't fall out. And I'm not advocating that we come up with the ontology to end all ontologies. We had a lot of movements in that this is the ontology for design, ideally based on my understanding of design, and then you adopt this and then we'll all communicate happily. It's very much something which can get negotiated, needs to get negotiated on a local level so that people understand it. But what people also need to know is the maturity of the method. So is that something that I can really trust that it will work, or is it just something experimental that might help me along? And they need to have a chance of exploring new methods so that it's not something where we ossify established methods, but we give people a chance to explore very broadly. And we don't want rigid methods, we want a very rich ecosystem of methods. And we also can have multiple alternative ecosystems, just as we have a desert and a coral reef. We have got multiple systems that often are around particular CAD systems or particular national traditions, and that's all right, they don't need to be all the same. But this is difficult in a transdisciplinary setting because often fundamental concepts are not quite clear to the people who are using them. So just to give you a very brief example, if we think about what is a model to a software engineer and what is a model to a mechanical engineer, it can be quite different because models, of course, are abstractions of reality that leave things out, but what they leave out is totally different. So for example, in a software model, we have got a very clear description of the abstraction on which we're operating, but it's leaving out all of the implementation details. Whereas on a model in mechanical engineering, a geometric model, we have a idealized description of it, but we're leaving out all of the manufacturing variability, all of the wear and tear of the system and many other elements. And of course, unless you're familiar with this, you don't know what to interpret into it. If you're familiar with it, it's blatantly obvious, but it can be a challenge in that kind of collaboration. So what we do need is an understanding of how disciplines work together, but there is surprisingly little comparison between different engineering disciplines. I mean, here also you talk about transdisciplinary design, but without working out exactly what's different between the different fields that you need to be trans about. So there have been various attempts to look at comparisons, but they normally end up with generic principles or are very specific on particular topics, and both of them can be a problem. But there are also other disciplines that look in that have got generic approaches, and that's, I think, why I'm going to tell you a little bit about epistemology of technology, because that again is looking across a broad range of different topics. Now, if we think about what do engineers know, it's actually a very complicated question. I mean, most of us are academics, so we are in the business of knowledge. And we teach knowledge and convey knowledge, but really thinking about what does engineering knowledge mean is actually quite a difficult question, but it might help us to understand why this method issue can be so difficult. So we've got different ways of looking at engineering knowledge. Philosophers never agree with each other, so they've got multiple classifications of things. So we have the very classical know-that, know-how distinction, which I think very much entered that public speaking, but we also have got different aspects to know-how. For example, Hauke's definition of both the procedural knowledge, so the sequence of the action, but also this operational knowledge, which is the skills you need in order to carry these things out. And that comes quite close to what we mean with methods, that we need both the skills, but we also need the sequence of the activities. But I'm going to go into a bit more detail about one of the richer classifications of engineering knowledge, which is from Walter Vincenti, which is what engineers know and how they know it. He was an engineering professor at Stanford who basically tried to explain engineering to his academic colleagues, and I'm sure many of you will have tried to do the same thing and found this a bit challenging. So he decided to sit down and write this book. And he came up with a number of fundamental categories of engineering knowledge. So he has I'm going to go into detail about some of them, but he basically has got a fundamental design concepts. This is sort of basic configurations of aircrafts, which you see on the title page here. We have got criteria and specifications. We have got quantitative data. In the moment, we have got quantitative data galore. And there are theoretical tools, which is often what we learn at universities. We have practical considerations, and we have got what he calls design instrumentalities. And before I go into detail, maybe just as a bit of context, this book was published in 1990, but he was basically an aerospace engineer around the Second World War. So he had a very rich engineering experience, but that was before the method tradition really hit the United States. So this formalized method thing has very much come out of Germany. And that essentially entered America when a lot of these German books finally got translated into English. And he also did this work before digital tools really took off. And of course, big data was far away at the time. And the problem with methods is that we think that they don't quite fit into this classification, that they are a category of their own because they go beyond several of the categories. But I'll unpack some of the categories because they show up some of the differences. So we have got theoretical tools as a category. That's very much the sort of underpinning of fields. It's the mathematical and the physical theories. And those are very different in different fields. So a mechanical engineer will have different theoretical underpinnings than a computer scientist. And they don't necessarily know what the other ones know. So things that are blatantly obvious to one field might not be clear to another. I mean, for example, we might all think that people know how to transform matrices, but that might not necessarily be the case. And then they can't use the method because they don't know what to do with their matrix if they find one. And also the theoretical tools don't really carry the explanation about how they are supposed to be used and when they are supposed to be used. So that's extrinsic to that category of knowledge. And there is very much a general assumption that the theoretical tools are likely to produce consistent results, like we are all assuming algorithms will give us a reliable result, so other theoretical tools do as well. And I think realistically in all of those knowledge categories, universities are in the business of teaching theoretical tools, and we're trying to figure out how to teach some of the other categories. I'm getting there, honestly. Then we have got another category called design instrumentalities, which is covering essentially a lot of the sort of cognitive processes and experience that people are having. Their analogies, their visual reasoning, and that is very personal and very context dependent. That is taught in some cases, but not necessarily in all universities, and it's taught in a different way. And that is definitely not shared across different disciplines. And then we have got practical considerations, which are the sort of rules of thumbs, the experience of the people. And again, that is very personal and very different between people in different disciplines. So if you think about this, we have only got very little overlap in those categories of knowledge that we can draw on in order to come up with methods. So we think essentially that we need methods as its own category of engineering knowledge. So where we have got the knowledge of the procedures and the procedural knowledge, and we have got the linkages to other kinds of categories. Now, the other question is whether we understand method very clearly. So I'm not going to go into detail, but we could also look at the knowledge categories and see whether it helps us to sort of tighten up the notion of method in our own community, but maybe that is for another time. So I think I just want to conclude to say that what we really need is a way of developing transdisciplinary methods. So we need the common vocabulary and the common understanding, and we also need to have a signposting for the theoretical tools that people are using so that they can say, look, this is something I take for granted. I assume this. If you want to work with me, this is something you need to learn, or this is something we need to take over. But also, I think we need to get people to have a joint ownership of the methods. As long as we are in a situation where one discipline simply pushes a method onto its other disciplines, it's not going to work. People need to develop it together and say, yes, we own it, that works in our own organization, so that we get the power struggles out of the methods and have the methods not as a proxy battlefield for which discipline is top in an organization. And we do need to understand how our methods interface to the methods of particular fields. So we'll need transdisciplinary methods as well as monodisciplinary methods. And ultimately, I think we need our methods to actually help us to contribute to a common understanding of the purpose and the ways the system works, so that the methods don't become a distraction that people have to follow, but have become a way that empower people to work together. And of course, as academics, we also need to start thinking about how we can work together across fields to help industry to develop these transdisciplinary methods. So that concludes my talk.
Wonderful. I thought that given the breakfast buffet that we'd have too much. This is an idea buffet. Terrific. And really inspiring. And I'm going to ask you to please send me a photo of your bookshelf, because I have so many questions. So let's open for questions. And I think there are so many considerations about, I think, the keyword commonality and the distinction between transdisciplinarity and perhaps multidisciplinarity, and whether there's intentional heterogeneity, intentional entropy or not in this ecosystem. Let's see what you all have to say. Any questions? No surprise.
Thanks, Claudia. That was a really interesting talk. One of the dots that I'm going to join across into other parts of the transdisciplinary communities outside of engineering is that when they talk about interdisciplinary work and working across different kinds of communities, there's not just the intellectual work around how you make ideas meet each other, but there's an emotional work and around, I guess, issues of humility and these kind. And do you see that as well emerging in the spaces that you've explored?
Very much so. I think that's a very important element. And I was telling you about my friend in this engineering company, and she has a PhD in mechanical engineering, being an engineering company, but her mother is a nursery nurse, and she has children herself. And I think those parts of her skill set come in enormously, that she listens with great patience, dishes out sympathy, and tells everybody they don't mean well. They really try. They do love you. They just don't understand that you have to have an expensive test at the end. I'll tell them and they'll be all right. So it's very much this emotional understanding. And again, this is away from a power structure into a collaboration. That is an enormously important element.
Very good. Milton, did you have a question?
Thank you for such an interesting talk. I'm wondering if you could elaborate on how you would see this ecosystem of methods in a change management perspective, the role of middle and upper management to make sure that people understand the concept of this ecosystem of methods.
I think this is a very challenging social problem because, of course, there is power in the control of methods. And I think overcoming that mindset is difficult. My impression is that it's something that needs to get very strongly endorsed by upper management and pushed through as something that needs to be encouraged from the top so that people are accepting that they have to work on that. And that it's difficult if it comes from a sort of middle-out perspective or bottom-up perspective. But basically, I don't know either how to get this done. It's the honest answer.
Ira, how's your zone, Ira? Right side of the room, you have an obligation, so please come up with a good question. Until then, Bruce?
Hi, Bruce Hecht. Thank you, Claudia. That was really exciting to see the sort of landscape and the ecosystem model. And one theme I heard maybe had to do with different kinds of things that are learned, in different settings. You had before the theory, you had sort of mathematics as a tool, and then based on disciplines, the theories. And I was wondering, for the landscape that you're setting out, or this ecosystem, what do you see as some areas that could use improvement in terms of how we work together or learn together? And what would you like to see come forward from this community?
I suppose there is a lot of existing interfaces that are challenging. I think one of the big ones is between engineers and computer scientists, because in their case, the power balance is that they're almost weighed out, and you've got this playing out in car companies that is the car driving around a computer, or is the computer just supporting the car? So I think that is one of the big battlegrounds. But I think what this is important is to take this forwards as we go into big data and data science, because we have an opportunity to get it right by bringing new people in to start with. And I hope we're going to really take everybody along on this journey. And in the moment, we are seeing that people are appropriating techniques from machine learning, from data science, and do it themselves and don't talk to the domain experts. But eventually they will have to bring the domain experts in, and then I think they will struggle. So it would be great if one could do it together.
Going back to the Hawthorne experiments in Taylorism, there is great economic value and power around commonality. And the notion that we might have intentional heterogeneity or intentional entropy in the system is counter to a century and a half of industrial development. So you mentioned, in fact, in the 1990s, we spent so much time looking for the ontology of ontologies and kind of commonality. So how do we have you seen examples of how the culture or the mechanisms of the company of the industry have prevented commonality that would be undue, or to keep that ecosystem vibrant by having it be less coupled, I guess?
I think I totally agree with you that it's a really big challenge, that too much commonality stifles things and too much heterogeneity is inefficient. I think the challenge lies in getting a sufficient overlap that you don't end up with being islands. And I mean, one of the big cases for this is Airbus, where you've got the national cultures having to try to somehow or other negotiate it, and ultimately it has to fly. And I think there you have got different understandings of different elements working reasonably well. But I get the impression the show is kept on the road by a couple of people who can translate between these different approaches and put the things together at the interfaces.
Yes, Chadwick, Ira, go ahead.
That's not the mic. Hi, Chad Holmes. I wanted to ask, actually, you just hit on something that was a question I had. Do you see the future of this ecosystem coming together being driven by people who serve as those bridges, the people that actually become the transdisciplinary translators because they have feet in multiple disciplines? Or is it by creating systems that enable people who are deep in one discipline to work together? Is it going to be driven by the systems of the people?
I expect where it's largely driven is actually by the CAP developers, because I think we've developed ecosystems around common computer models. And I think they are probably the most powerful group to get this together, because they force people through their tools to work in a relatively harmonic way. But I think it's a problem that needs to get tackled from all directions. And I think us as academics need to look at ourselves and talk to our computer science colleagues and things like that. But I think it just needs to get approached from many levels, and then maybe it will improve.
That's interesting. So you just introduced a third one, then is platforms.
Yeah, exactly, platforms.
In that light, one of the things I'm curious about now, generationally, I'm from software, is that the form of software allows us to easily wrap or create artificial constructs which substitute for dependencies in relationship. I wonder if you've talked about commonality and building commonality, and if we think about that socio-technically, is this next generation, especially of software types, impatient? Are they very impatient, and therefore that leads us to not actually developing vibrant ecosystems?
I'm sure you're right, but I don't know whether we can afford to be patient, because, of course, in a way, the product development system is being pulled along by the speed with which the market wants products. And we ought to be far more proactive. And in my other incarnations, I preach at the academic community that we need to look forwards to the technological trends, to anticipate the methods, that we need to have them ready when the companies would actually use them, as opposed to let the company struggle, observe the struggle, apply for a grant, develop a method, and then hope that the problem will come away when the technology is no longer state of the art. So,
very good. Well, listen, please join me in thanking Professor Eckert for this terrific keynote.